This episode of Science Max Experiments at Large is all about light and bending light to your will.
Right?
And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large. Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh. Well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh well.
You okay?
Hi.
Hi,
Anne.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're gonna challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is gonna be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay. Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm gonna challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right? So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Do you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out. I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would go. I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation! A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it.
Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light.
Shine it on the ball so that it's a little bit better illuminated.
And then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going, keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Try bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy, solved.
Wait.
What?
That was just the warm-up.
Oh yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
With something else written on it.
Wait, are you coming back?
Nope.
Huh, but I can't even see you from here. Like how am I,
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right, I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope.
Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface.
And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons.
Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then,
get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your 2 mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light, in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror, and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like.
The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television.
Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television and leave the room.
I solved Anne's first light challenge, seeing something far away, with a lens.
It says 71.
But now she's moved the ball around a corner, and now I have the solution.
Mirror. A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay. Go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. it's being internally reflected. And the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Oh,
Ann? Ann?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
Here.
Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back. I'll be
Okay.
back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh?
That is an X-ray, a picture we can take using this part of the spectrum.
We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared.
For those of you keeping score, that's this part of the spectrum right here.
Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now.
Hey, Sal.
Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil? Is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it. Okay, here we go. Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time, it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
Try yours. What makes airplanes, or basketballs, or people fly? It's air. As well as a bunch of other things that we learn when we try to make a giant paper airplane.
So that didn't work.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ho-ho! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast, because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom, where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide, and open it up. And here's the trickiest part. See how it's bent like that? You push it open like this, and this is called a pocket fold because you wanna make a little pocket and push it up against there. Fold it flat like this. Fold this tip down over there like that. Then fold it around the back side. Then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings, and ta-da, the Sky King paper airplane fold. Now, as Science Maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, Experiments at Large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. Uh-oh, that's never good.
Whoa, Phil, I'm so sorry. You okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents How to Fly Your Paper Airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. High pitch.
Great, great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah. Yeah? No. Yeah. Yeah is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Here we go.
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace science and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh, yeah, you're
And-
right. The ink doesn't go straight. It
Yeah,
follows the wing
follows
down.
the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right, and
generating lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay.
Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out.
I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Woo! Okay, be very careful getting off it. Woo! All right, let's fold it. Nose on that side. Okay.
Remember, we're folding the exact fold we did in the lab, only on a larger scale.
We have a tape malfunction down here.
But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
There.
Perfect.
Yeah. Giant paper airplane! Ha ha ha!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Yep. Maybe.
Like, I'll just.
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah.
Go for it.
Okay, here we go. Wow. What do you think?
Oh man.
I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look. Let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very, very floppy.
Very floppy. What if we supported the plane, like we put struts or something in it, like this stick? If we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like foam.
Yeah,
Stuff?
and like hollow tubes.
Hollow tubes. Good.
tubes.
Good. So we'll put a whole bunch on there. We'll tape them on so that it doesn't flop around.
Yeah.
We'll try it again.
Yeah.
Yeah, I think we got
Yeah.
something.
Okay, great. Let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the...
So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
There. And then that. Great, look at that. It's not even flopping around. It stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be, well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just...
Phil, there's a lot of stuff on here.
There.
But like it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, let's do it, let's do it. All right.
Okay.
All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, yeah, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do, and then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. Hey, Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah.
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up. And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour. All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour. Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly. Oh, woo! There you go, our Mark III model paper airplane. Now, I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap. But we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose.
We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Whoa, okay, all right.
Phil, that was great!
All right!
This throw worked best, but I know what you're thinking. Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is
Largest paper airplane I've ever thrown! Woo! You guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large. Where were the stairs? Yeah. Oh, never mind, I found them.
Today on Science Max, we're using the forces.
Pendulums are pretty simple. It swings back and forth.
Marbles, dominoes, sledgehammer, trebuchet, rockets, levers, rockets, tension, and that's just the main experiment.
Maxed out dominoes.
I love that idea.
All this and more on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. Today, we're going to be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're going to look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machines. Rube Goldberg machines. Rube Goldberg machines. Rube Goldberg machines. Rube Goldberg. You heard me say Rube Goldberg machine. Okay, we got that part. Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out. It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big, heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off, and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay. Hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1. Sonia!
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble. and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia. Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
That. Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You
Can
want
I
to try
try
it?
it?
Please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go. Why didn't?
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes. I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will see.
Do they dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay, so
we
now.
started off with this domino. Then we went bigger.
Yeah.
Bigger,
Yeah.
bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then...
Here we go.
3, 2, 1. Whoa!
Nice. That was pretty far.
Yeah, check this out. Whoop. Okay, so
Nice.
now that we've got the trebuchet firing, and the ball is going over there, we need to get the ball going over here
Yeah.
to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over. on us.
Okay.
Now we're gonna talk about tension. What's tension? One more than 9-shin. Get it? Because tension and 9, that's, okay, because tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these nuts.
And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science. Sonia and I are maxing out a Rube Goldberg machine. The first part worked pretty well, and now we need to change the ball's direction. This is a trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now, I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way. The one thing you need most of all when making a Rube Goldberg machine is patience. Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So, not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh, yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap,
Oh.
and...
Ah, so then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
Yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what'll happen? It will fall. Yes, that's right. It'll fall because of gravity, but watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. And when it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out.
this is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that.
Whoa, super maxed out! Science!
Sonia and I have used potential energy, the lever, and chemical energy.
But you know what one we're missing?
What?
Is electrical energy. Electromagnetism.
So watch, the chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall and flick this switch. See that sledgehammer? This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready?
There.
There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try
let's try it. Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked. The chemical rockets fire, and they hit the tray.
All right. That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, button, cake.
I have an idea.
All right. Cake any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. Sonia has added one more step to our Rube Goldberg machine, a stomp rocket. It's a hammer rocket.
Exactly.
I like
So
that.
what's gonna happen is the hammer is gonna hit our bottle, which is gonna release all that air that's built up inside of it. It's gonna hit that button,
Wait. The rocket hits the button.
and then we get some
Cake!
cake.
Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1. Oh.
Yeah.
pause here just before the cake portals in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap, which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our stomp rocket with it. The stomp rocket flies through the air and hits our cake button, which then portals in some cake.
Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
But,
go.